In this talk, I will be presenting our work on accelerating deep learning recommendation model training. This is a joint work with Chaoliang, Xiaodian, Han, Xinchen, Hao, and my advisor, Professor Chen. Deep learning-based recommendation systems have been widely used in many online services. This is a high-level architecture of a typical deep learning recommendation model, which consists of two components. One is the embedding table, and another one is a conventional MLP stack. As a major characteristic of the deep learning recommendation model, it splits the input into dense features and sparse features. For sparse features, the embedding model uses an embedding table to project the categorical sparse features into the computable embeddings by looking up the embedding tables with the keys of the sparse feature IDs. Then the retrieved embeddings are fed into the neural network along with the dense features. During the inference or training, it looks up the embedding. It looks up the embedding table to fetch the embedding features. So there are two characteristics in this training architecture. The first one is the large memory capacity, because we need to store, it requires hundreds of gigabytes or terabytes memories to store the embedding tables. The second one is we need to get large number of computing capacities for the increase in model size, especially we need to several GPU devices. So to satisfy this hybrid requirement, existing training systems decouple the embedding table lookup and the MLP processing. Specifically, they utilize the compute-optimized GPU workers to accelerate the MLP processing and use the memory-optimized CPU servers for the embedding table maintenance. During the training, GPU workers keep fetching and updating embeddings to the parameter server via the network fabric. So the overhead of these two embedding transmissions can be significant in the BST training due to the frequent embedding fetch and updating. To mitigate the above communication overhead, common practice designs embedding cache to cache the hot embeddings in GPU memory locally, which helps to reduce the network transfers of the embedding fetches and updates. However, naively adopting the cache system in the distributed embedding training model still suffers from the significant communication overheads between caches and the parameter server. We study 4 workloads with a testbed containing 8 workers and 1 PS over 100 gigabytes Ethernet fabric. The results show that embedding communication can contribute up to 63% of the end-to-end training time. There exist some attempts to further reduce the communication overhead by optimizing the cache-based systems. They either oversample the training data containing only the hot embeddings with the fast inter-server collective communication, or applies the staleness-tolerant embedding updating method. However, their optimizations may hurt model accuracy due to the deviation from the BSP training. But in the production environment, a reproducible and high model accuracy is important and desirable. So, in this paper, we seek to figure out a way to reduce the embedding communication overheads without compromising the model accuracy during the training. To achieve this goal, we first revisit the cache accessing behaviors in the embedding training, focusing on the network transfers resulting from the worker pool. Here is an example. When all GPU workers are fed with inputs that cannot find in the local cache, they need to pull the corresponding embeddings from the parameter server. So these bad cache accessing behaviors lead to significant worker pool transmissions. However, there's an opportunity to avoid these worker pool transfers. If we permutate the input batches properly at a cache-friendly manner, we find all workers can train a sample with the cache embeddings. So there is no worker pool transfers in this scenario. So in this paper, our theoretical analysis proves that this permutation can preserve the model consistency and thus deliver the same mode accuracy as the vanilla BSP. In addition, we also revisit the cache behaviors in the worker push. Following the previous example, after the GPU workers are trained with these samples, they need to synchronize the local updated embeddings with the parameter server. A Liao solution is to push all updated embeddings, while it may introduce USENIX transfers. Actually, we only need to push some necessary embeddings to the parameter server, which are required by other workers in the following iterations. Here is an example. We find that only embedding 2 is required by other workers in the future iteration. Therefore, only the mid workers need to push the updated embeddings into the parameter server. Other transfers can be avoided. So it leads to another opportunity. We can do on-demand synchronization. We find that the necessary embeddings that are required by other workers in the future iterations, we find only in the left and the middle workers need to push their updated embeddings to the parameter server. This implies that the worker push transfers can be optimized by performing on-demand synchronization. In addition, we make 2 observations of the in-cache access behaviors. First, the cache access behavior is predictable since the cache snapshots of each worker is observable and the input partition can determine future embeddings, accesses, and the cache behaviors. Second, a specific embedding is accessed infrequently, which means that although a small set of hot embeddings could contribute to the majority of the total number of accesses, the accesses of individual cache embeddings is usually infrequent. To understand the degree of the infrequencies, in this figure, we refer to the DOI. It means the ratio of infrequently accessed embeddings over the whole embeddings in cache embeddings. We make profiling on the 4 datasets as listed in previous tables. We find that over 90% of the in-cache embeddings are accessed infrequently. So there's an opportunity that we can train these infrequent embeddings in one consistent server. Based on the above 2 observations, we propose embedding scheduling, which proactively determine which embeddings should be trained and which embeddings should be synchronized. To answer this question, we revisit how to avoid embedding transmissions during the training. First, cache hitting can avoid cache pull from the PS. Second, if we update the embeddings are not required by other workers in the future iterations, we can avoid pushing these embeddings to a parameter server. Therefore, based on these ideas, we summarize 2 scheduling philosophies. The first one is that we want to train in-cache embeddings as much as possible. The second one is that we want to perform synchronizations when necessary. When considered the whole deep learning composition model training data flow, it's important to make the embedding scheduling decisions in real time for 2 reasons. The first one is that it's really difficult to process the whole data set in advance. The second reason is that the number of training iterations is unpredictable because normally we stop the training only when the accuracy meets our goal. So the actual number of iterations of the embedding scheduling is unpredictable. So there are some challenges of the real-time scheduling. First, there is a trade-off between the scheduling quality and the scheduling overhead. High scheduling introduces longer time. And second, the scheduling budget is not static because it's affected by many factors ranging from the data set or the per work batch sizes. Therefore, this calls for an adaptive scheduling algorithm because we need to satisfy the runtime scheduling budget of the embedding scheduling process. According to our scheduling philosophies and motivation for the online scheduling, we designed Herald to incorporate embedding scheduling to the recommendation model training. Herald is a plugin of the data loader. The previous challenges are addressed with a decoupling idea. In general, it applies the location-aware input allocation to determine where embeddings should be trained. And it contains a process to generate the communication plan to answer which embeddings should be synchronized to figure out the embedding dependencies among the workers. The location of where input partition handles a batch of embeddings based on the cache snapshots. If we output the training samples with the embedding dependencies for every worker with a heuristic algorithm, we illustrate this process with a simple example. Here is the 3 samples in a batch. We need to distribute the 3 samples to 3 GPU workers. First, we need to compare the cache capability between the input samples and the local cache in each GPU workers. For example, for the sample 1, and we compare its cache consistency with the GPU worker 1, we find that 80% of its training samples can be found in the local cache. Similarly, we can find the cache capability for other samples. So in this case, we will dispatch this sample, the first sample to the worker 1. And similarly, we can continue this process to dispatch another sample to other workers. After this process, ideally we want to find the best allocation for the input batches. Each GPU worker needs to only fetch a small number of embeddings from the remote premise server, which are not cached locally. As illustrated above, hurriedly to deal with the limited and varied runtime scheduling budget. To solve that, we observe the distribution of embedding popularities is different. In different tables might exist schoolies and diverse degree of infrequencies. Therefore, to accommodate the potential limited scheduling budget in real time, we adaptively pick up the tables with higher scheduling budget and comparing the dataset batches and cache snapshots. After partitioning the dataset, the input of the worker include 2 parts, training samples and the communication plan. The communication plan enables the on-demand synchronization. To get a communication plan, we can infer that we can find the dependencies at the next iteration. Because we also illustrate this process with the example. After iteration X, we find that worker 1 only need to push embeddings that are required by other workers in next iteration. In this example, it's 0 and 1. Similarly, we can figure out other necessary embeddings need to be pushed to parameter servers as following the same processes. This is the evaluation setup. Most of the settings has been mentioned before. We compare Herald with HET training with vanilla BSP to preserve the same model accuracy. First, we use micro benchmarks to understand the effectiveness of the adaptive location of where partition algorithm. We find that the number of tables that NIA can be considered during the scoring to strictly meet the scheduling budget with the increasing number of workers. We also find that adaptive NIA introduced less than 1.11 times transmission increase by scoring with at least 4 tables, which indicates Herald is scalable and adaptive to different scale of training clusters. In the end-to-end example, when compared to HET, Herald can achieve up to 2 times speed up over TCP and 1.6 times speed up over RDMA. This speed up contribute to the communication reduction in the number of embedding transmissions. We also evaluate Herald in a multi-GPU, multi-load testbed consisting of 10 servers as workers. Each of them contain 8 GPUs and 80 CPU cores. By comparing to HET, Herald can achieve 1.02 to 1.6 times speed up among 4 workloads. For more experimental results, please refer to our paper. Finally, I want to conclude with recoupling Herald. First, we explore the embedding scheduling as a Liao acceleration direction for the neuron recommendation training by leveraging the characteristic of the in-cache embedding accesses. Second, we design Herald, a runtime embedding scheduler to reduce the embedding transmissions with the location of where input allocation and on-demand synchronization. Besides, the recommendation model, we believe Herald can be extended to accelerate general embedding models training in the future. We have open sourced Herald on GitHub. Thanks for listening. I'm glad to take questions.